Hello, everyone, and welcome. I'm Allan Jude, your host for today's session, and whether you're joining us live or watching the recording later, we appreciate you joining us. For those of you who are new to Clara, we're a team of open source experts who specialize in ZFS and FreeBSD and helping companies worldwide to optimize their systems and tackle complex technical problems. And so if you have any of those, you should talk to us, including if you're looking to do something like re-architect your storage pool, figure out how to squeeze more performance out of your ZFS or FreeBSD infrastructure, or if you'd like to develop a new feature for ZFS or FreeBSD, then please do get in contact with us. Now, for our webinar, in today's session, the right way to benchmark ZFS, avoiding pitfalls and misleading metrics, we'll talk about some common mistakes people make while benchmarking ZFS, how to design a benchmark that will reflect your real-world performance and your real-world workloads, why ZFS caching, compression, and copy on write have impacts on your benchmark and how to compensate for those, and finally, recommending some tools and methodologies to get meaningful performance analysis when you're benchmarking ZFS. Throughout the session, feel free to drop your questions in the chat or the Q&A system in Zoom, and we'll be monitoring both those and some of the questions that were submitted during registration, and we'll be answering them as we go. And then joining us today is JT Pennington, so I will pass it over to him to start with introductions.
Yep. So as Alan mentioned, I'm JT Pennington. I'm one of the ZFS solutions here at Clara. I work with clients to help deploy and implement and tune performance on their ZFS systems. And of course, Alan.
Yeah. I'm a co-founder of Clara and our principal solutions architect, so helping customers design and architect their storage systems to get the most out of them. So in today's session, after the introduction we just completed, we're going to get straight into the things that impact your benchmarks and why. So we'll talk a bit about caching and how that can give you misleading results in your benchmarks, how compression and zero elimination can really gum up the works, and then the biggest mistake we see is misaligned record size. And we'll show what that looks like and how to tell when that's happening so that you can deal with it. Then some other common gotchas, like the fact that ZFS can write behind what you're doing, and that can make it look like it's faster than it is, or otherwise throw off your results. That's why you also sometimes need to have a rest period between benchmarks to make sure the system actually gets back to idle. And then we'll talk about some best practices and kind of throughout, and at the end we will cover more Q&A. And then we'll make sure that you know how to get in touch with us if you need some help with your ZFS performance. So jumping straight into it with caching. And while, when deploying in production, caching can be a big benefit, right? It can really improve how much you get out of the system. But during benchmarks, it can actually give you pretty misleading results. If your sample size is too small, they can make it look like your system's a lot faster than is even physically possible. And at the same time, really mess up the results. So looking at this, when benchmarking, just covering some best practices, the first thing is you always want to be testing the worst case scenario. When you're testing the worst case scenario, not the happy path, you ensure that you're giving the benchmark of where the system will always perform at least this well, right? If you're testing, all the things turned up to the max and you're making sure that everything that can go wrong has in this test, you know that no matter what's happening in the real world on your system, you're going to get at least this much performance. And if it's better, that's great, but you know it's never going to be worse than that level. Whereas if you benchmark the happy path, where there's nothing else running and you're just doing this one thing at a time, then you're going to have expectations that the system's not going to be able to meet in reality, right? If you're testing just reading when nobody is doing anything else on the machine, how often is that the case in production where there's not 7 other things also happening on the system at the same time? And so you really want to test the worst case so that hey, if we test it with really small blocks, then we know even if the blocks get bigger, the performance will be at least that good, if not better. And the other main thing is that we want to check the results that we get at each step, right? Down each level of the stack to make sure that while the benchmark says we're doing this many megabytes per second, how much does ZFS think it's seeing? How much does the disk think it's seeing? And each step all the way down the stack to make sure that the numbers match up. And if they don't match what they should, then you want to look at why and understand why the benchmark is giving you a different result than you actually expected. So if the result seems too high, then it's important to ask why. Right? If you are benchmarking a hard drive and it's claiming to do a gigabyte a second, and you know the hard drive can only do 200 megabytes a second, then obviously the result is wrong, but you want to figure out why and fix your benchmark so that it doesn't give you results that don't make any sense. Because all benchmarks are synthetic, right? We're attempting to model something that happens in the real world and eliminate some of the complexity to get a reproducible and repeatable way to test it, but it's never going to be perfect, right? We're always going to be making up the workload. And so we want to make it as bad as possible so that, or as difficult as possible for the machine so that the result we get is the worst case scenario. It means that, in production, it'll never be this bad. It'll always be a little bit better than this. And so you'll know you'll always get at least this performance, if not more, instead of the other way around, where it's like, well, the benchmark says it can do this, but when we try to actually, stream video while somebody's editing, then we see the performance is much worse. So now getting straight into caching and how that affects things. So ZFS has an adaptive replacement cache, and it's designed to improve the performance of ZFS and make up for the performance trade-offs of copy on write. Because of copy on write, whenever we're changing something, ZFS is doing more work than most other file systems. And it's kind of spreading the file out across the disk, which, especially on hard drives, can be slightly worse because it involves more seeking and less streaming reads. To make up for this, the ZFS ARC and the prefetch and the other features we'll talk about today work to make up for that fact. But during a benchmark, you want to assume the worst case where the cache wasn't able to help, and you have to know what just the hardware can do without the help of the cache. So when you're performing benchmarks, the cache will always skew the result, right? If your result is too small and the entire thing fits in cache, then the first time you read a block from the file, it'll be the speed of the hard drive, but the second time you read the block, it'll be the speed of RAM. And that will result in performance that is a lot better than is physically possible out of the, your spinning rust or whatever. And so that's why you want to make sure that the cache is either off entirely or set to metadata only. Because of the levels of indirection and so on in ZFS to deal with dynamically allocating all the data structures, caching the metadata is usually worth it. And even if you have a lot of data, the metadata is quite small. And so you can assume, even in the worst case, that you're going to be able to cache all of that. And it does make a difference to the performance, especially if you're reading very large files like FIO does. If you're doing a bunch of 16 gigabyte files across threads, caching that metadata will save a lot of IOPS over not. But you still want to make sure that the data reads that happen are still actually going to the media and not coming from RAM, because you're trying to benchmark your file system, not your RAM. So JT, you have an example here that came up.
Yeah, so another important thing to keep in mind is that the ARC cache that we've been talking about is set on a dataset level. So when you are creating the dataset to do your testing on, you need to make sure that you do set the primary cache accordingly. It will, by default, ZFS will inherit whatever the parent dataset has set. So you'll want to explicitly go in with the ZFS set command and set the primary cache to either off or to metadata. So in this example, we're doing a simple read test of a data set that has a whole bunch of files in it. And you can see that we are reading at over 2 gigasecond. And the first time you see this, you're gonna be like, oh, this is great. My system is performing fantastically. But if primary cache is set to all, you're not actually reading from the disks. You're reading entirely from RAM. And we can see this by looking at the output of zpool iostat. If we pull that up, we can see that the third column that's listed here is
The one I highlighted in green.
yeah, the one highlighted in green is the column that would be the bandwidth for reads off of the drive. The first column that's not of zeros, that's not circled, that would be the IOPS for the drives or for the pool. So as you can see that right now we are reading at 2 gigabytes a second, but we're not actually reading any data off of the disks, because if we're reading data off the disks, the data would be shown right here. So what does this look like in this exact situation with this system and these drives when we are reading directly from the disk? Well, we get a much lower figure, as one would expect. So once we read from the drives themselves, we're reading at just under 300 megabytes a second. And we can see, and again, in zpool iostat, the fact that we're pulling at that rate from the drive, and we can see it's the fourth column in the image, the 72,000, 72,000, 72,000. That is the IOPS of the drive. So we know that we're actually pulling the data off of the drive to read this data.
Yep. And so that's how you can tell that, the results you're getting matching up what the hardware is actually doing. And if there's a big delta in between, then either there's more work happening on the hardware than you're getting, which is another case we'll talk about later. Or if the disk is doing less than the result you're getting, then something's up. That might be because compression, right? If the data is compressed 2 to 1, then you're only going to have to read 150 megabytes a second in order to actually read 300 megabytes a second once you decompress the data. But you always want to be comparing the results of the benchmark to real-time observation of every level of the stack. So in this case, zpool iostat, but also like iostat or gstat or something to look at what the hardware is doing underneath, or even just zpool iostat-v to look at each individual hard drive and make sure that what the hardware is doing underneath is matching up with the results you're seeing. And that if it's not, you want to figure out why. There might be a good explanation for why, but it might be that caching is interfering with the results, or compression is mutating the results, or as we'll talk about later, right behind means that it's not going to the disk at the same time that it looks like it is. So speaking of compression, we can talk a bit about that, because it turns out, especially in a benchmark, that doing nothing is really, really easy. So ZFS has an optional transparent compression feature, and it became the default that LZ4 compression is enabled, starting with version 2.2 of OpenZFS that was released back in October of 2023. And so that's what's included in Ubuntu 24.04 and later. But basically this means as you're writing data to the file system, ZFS looks at the block, and if the entire record, whatever your record size is, the default is 128K, but if that whole 128K is all zeros, instead of writing that to the hard drive, it notes that, hey, that's a hole. Basically, that this entire thing is sparse, and it doesn't have to write anything. It just keeps a note that, that range of 128 kilobytes exists, but it contains nothing. And so it can just make up those zeros in memory next time they're needed, and you won't have to read from it. But if, like a lot of benchmarks, your benchmark tool writes all zeros to the file system, if compression is enabled in ZFS, it will see that and just delete all of it. It'll accept all the zeros from the application, see that they're all zeros, and just make a note in its metadata that that block is all zeros and not have to write it. So you'll be writing 30 gigabytes a second with your FIO benchmark, and then when you check zpool iostat, it's doing a couple of kilobytes of metadata, and that's it. And if your real world workload is writing all zeros to the hard drive, yes, ZFS will perform that well. But it's likely your real world workload isn't just writing zeros to a hard drive. And so, yeah, a lot of benchmark tools default to that, which is fine. You can disable this behavior in ZFS by just setting compression equals off on the data set that you're benchmarking, and then it will actually write out the zeros like you asked. But, you have to be looking at the zpool iostat and the hardware and make sure that the results are what you expect. that it's not eliminating all the zeros or whatever. Or especially if you're using a benchmark like FIO, it has the option to set the compressibility of the data. So FIO can generate completely random data that won't compress, or it can create data that's 60% compressible. And then ZFS will compress that down, and you will see that while you're writing a gigabyte per second, if you're compressing it to 60% of its original size, then the hard drive's only going to have to write 600 megabytes a second to achieve that 1 gigabyte per second. So maybe with 3 hard drives or a 4 wide RAID Z1 or something, you'd be able to achieve that, even though those physical hard drives couldn't actually handle writing a gigabyte per second. So yeah, if compression is enabled, ZFS will compress or eliminate, if it's all zeros, the blocks, and that could result in your benchmark giving you more favorable results than is in actuality. And again, that's why we usually benchmark the worst case, right? We benchmark with uncompressible data, meaning that we're going to get no savings from doing the compression. In the real world, maybe we'll get 20% compression. And so we'll actually have a bit more bandwidth out of the disks than we did in the benchmark. But, going faster than you expect is good. Going slower than you expect is bad. So you want to set your benchmark on the worst case. Otherwise, you end up getting performance figures that you won't actually achieve in the real world. And then your benchmark is not really helping you.
Yeah, and the last thing you want to do is implement a system and go to your superiors and be like, look at this great performance I got from all our testing. And then you put the system into production and it does 25% that. And now you have to answer for why is our system not performing like you said it was going to perform?
Yep. So one of the most common problems we see with benchmarks is that most benchmarks default to testing small blocks because that is the hard scenario, right? That's the worst case. But ZFS defaults its record size to 128K. And so you get this kind of square peg, round hole problem where those two things don't really add up. So when you write data to ZFS, it's going to break up your big files or big streams that you're doing. If we're using FIO and testing with 16 gigabyte files, one per thread, and testing with 16 threads or something, it's going to take that 16 megabyte file and break it up into chunks. In this case, by default, 128K. And then compression is applied to each one of those chunks if it's enabled, and on and on. But if you're doing a full random write workload using FIO, then you are going to take a 128K block that FIO laid out at the beginning of the benchmark, and then you're going to update just the middle 4K of a 128K block. And so under the hood, ZFS is going to have to read that whole 128K because you've disabled the cache, right? And then modify it in memory and update just the 4K of it. But then it's going to have to write out that whole 128K block and the metadata that points to it to update its checksum and up and up and up all the way up the tree. So now every 4K that you're writing is actually making the hard drive do 128K of reads and 128K plus a little bit of writes for each 4K you're doing. And so it's going to massively balloon the amount of work the system is doing. And it can mean that you get a result that looks terrible, very pitiful, but it's because you're actually making the system work harder than you meant to.
Yeah, this is sometimes hard to explain just how bad this can be. So we have an example to really kind of hammer this home. As you can see, we're running a write test here, and the test is writing at 30 megabytes a second. That's what's circled in green up there at the top. But if we look at ZFS and what the pool is doing, we can see that in green, we are writing a gigabyte a second of data to the disk. And we are reading, that's what's circled in red, 750 megabytes a second. So to be able to write 30 megabytes a second to disk, we're actually doing about 2 gigabytes a second of actual data transfer to and from the disk. Obviously, that's going to destroy your performance because you see 30 meg just on the user front end, and you're like, man, my application is really slow. And if you check the system, you'll see that your hard drives are just going crazy. And obviously, that's not the way you want your system to be set up. And with testing, you don't want to test that scenario. Now, the question is, what does this look like if we actually apply the same block size to the same record size in our write? And we have that example for you.
Yeah. So the other thing I wanted to quickly explain is why there's such a difference between the read and the write side. And that is when reading the data, when we're reading that 128K, ZFS can skip the parity, right? Because if the reconstructed 128K block passes the checksum, we don't need to read the parity. But when writing, we always have to write the parity as well. And so in this case, we are the most we could actually expect out of this was probably 700-ish megabytes a second. But because we're making it read and write, we're chewing up all the performance of the system just to do 30 megabytes a second of work. And like JT said, we're generating basically 2 gigabytes a second of load on the hardware just to do that 30 megabytes a second because we're doing these sub-block updates. Whereas when we compare to the case where we are testing with aligned data, right, 4K blocks out of FIO, but to 4K records in ZFS, the results are magically much different.
Yeah, so in this case, you can see that we're writing at over 500 megabytes a second. And if we look down at the ZPL IOSTAT output, you can see that our writes here are about what we would expect. And our reads, more importantly, our reads are low. We're only reading a couple K off the disk. The other thing I'd like to highlight here is, Alan, actually, if we can go back one slide.
Mm-hmm.
So if you look at the total IO in the right section above the image, where you have IO equals 3,633 megabytes, this is the amount. This test was done for 120 seconds. This test was run. And in that 120 seconds, we were only able to write just shy of 4 gigabytes of data. Now, if we go to the next one, which is the properly aligned, you can see that this same test, the same 120 seconds, but properly aligned, throughout the entire length of the test, we were able to do 66 gigabytes of data. So we went from under 4 to over 60. This is really, really important to get right when you are testing, because otherwise the results that you're going to get are going to be completely unhelpful.
Yeah. And like we talked about, again, this is the worst case, right? Because we're doing the smallest possible block of 4K records. And you see, because of the metadata overhead and so on, ZFS is still writing almost 2 gigs a second most of the time in order to achieve that 500 and something megabytes a second. Whereas if we instead had turned this benchmark the other way and had FIO do 128K blocks on top of ZFS having 128K records, we likely got a lot closer to 1.7, 1.8 gigabytes per second after you account for the parity of throughput. But if your workload is going to be a database that's only going to do 4K or 8K or 16K blocks, you don't want to benchmark 128K. But if your workload is, copying very, very large data files that you mostly only read, then you might even go further and have your record size at a megabyte. But whatever your workload is and whatever record size is going to work best, you want to benchmark where you're matching what the dataset does. But also it means you want your benchmark to model what your workload does, and then you want ZFS record size to match what the workload does. And when you line those three things up, you will get much, much better results instead of not. But this also raises the other question of, if we're writing 500 megabytes a second, how come sometimes we see a lot more writes, but also sometimes we see a lot less writes? And that leads us into the question of write behind. So ZFS does batching and aggregating, right? So there are two types of writes in ZFS. A synchronous write, which is the special kind, we'll talk about that in a second, and asynchronous writes, which are your normal writes. So most times if you're saving a file in an application, you're copying files between directories or something, anything like that, that's an asynchronous write. Basically, the application says, hey, operating system, go write this data for me. And immediately the operating system says, okay, and the application goes on and does its next thing. But there are times when you want a guarantee. For example, if you're a database application or a certain specialty application, when you go and write data to the operating system, you will either, as part of the write or afterwards, say, and now tell me once that data is safely on disk and will survive a reboot. Right? So in a database, it's very important, right? You're doing transactions or something, and you don't want to tell someone that their order is recorded until you're sure that even if the system reboots right now, the order will still be there when the system comes back up. So with those synchronous writes, that asks ZFS to do a lot more work. But with those asynchronous writes, we basically keep the data in memory, and then at the end of the transaction group, which is sometimes up to 5 seconds away, then we write out the data onto the hard drive so it's persisted. And so that means when the application writes the data and when the data goes to the disk might be a couple of seconds apart. There's advantages to doing this, right? In these transaction groups that ZFS uses, uh, a lot of workloads that say just append to a file or keep updating the same block inside of file, like multiple times a second, or just overwrite a whole file with a different data. If they do that many times per minute, ZFS can optimize things by only writing it out once every 5 seconds instead of writing out every version that ever existed. Right? If you're, updating a file 10 times a second, then if we only write it out once every 5 seconds, we're doing 1/50th of the amount of work. Because ZFS has to record the block and then also the checksum of the block and the checksum of the checksum of the block and so on all the way to the top of the tree, it's a lot of extra work to do all these writes. So only syncing it out when it's necessary every couple of seconds can really reduce the amount of work ZFS has to do and improve the performance of the system. And as I said, because it's copy on write, we have a lot more work every time there's one of these updates. So ZFS batches them together and does it more efficiently. So this can cause an interesting effect when you're observing ZFS in production. If you just run zpool iostat on a modestly busy system, you'll mostly notice the read column will be busy kind of all the time, and the write column will be mostly zeros, and then once every 5 seconds, there'll be a bunch of writes as it flushes all the pending stuff. And then it'll go back to probably almost zero the whole time. And then every 5 seconds, will be this blip. So that is how ZFS is supposed to work, and that's fine. But when you're doing a benchmark and you're using these same kind of asynchronous writes, we see this often with people like using DD, for example, to just write a file, then it'll finish writing the file and say it's done in, I wrote gigabytes in 7 seconds. But really, not all of the many gigabytes that you wrote have actually made it all the way to the disk in that 7 seconds. Some of them are still sitting in memory and are going to write out over the next couple of seconds. And so that can result in, the amount of data divided by how long DD ran for, telling you that you wrote X gigabytes per second when really you didn't. You wrote less than that. ZFS spread it out over more time. And that's why it's important to actually, in tests like that, have the application ask for that guarantee only once at the end. You don't have to ask for it after every single write. You don't want to, ask for a guarantee of every 4K. ZFS can do that, but it'll be a lot slower. But you can ask for it just once at the end. So if you're using FIO, then there's a flag fsync_end. When you enable that, it'll do all the writes normally just as fast as it can, not asking for any guarantees. But when it gets to the very end, it'll say, okay, and now I'm going to wait until you tell me that all of this data is completely on the hard drive and will survive a reboot. And, you saw in JT's results, even though he had this test run for 120 seconds, it actually took 126 seconds to complete because 120 seconds of writing as fast as you can, and then 6 seconds of waiting for ZFS to flush all of that right behind. And then once it was done, then it resulted in the right answer. So if you took this 66 gigabytes and divided it by 120 seconds instead of 126 seconds, you would have got a benchmark that says, oh, we averaged this faster speed that wasn't actually how fast the system went. And that, again, can give you results that are not realistic to what you were actually getting. So now to talk about some best practices and kind of recap what we've been talking about so far. So our first key takeaway is turn off caching. Want to talk about that a bit, GT?
Yeah, like we had covered, if you want to test your hard drives, you don't want to test your RAM. Yes, RAM is wonderfully fast. That's why we love it. That's why we use it. But at the end of the day, your data is going to be sitting on your drives, and you need to be able to pull the information off your drives. So that's what you want to actually test, because you want your test to be a measure of what you're actually going to see in production in the real world.
Yeah. So caching is, when you're benchmarking caching, you're really benchmarking how much faster it can be the second time you access a block. The first time you access it is still going to be the speed of your media. but the second time it'll be really, really fast. And so if you average that out, you get a result that you're never going to get that result. It is either going to be fast or slow. It's never going to be medium. Uh, and, if you are doing an FIO and you're testing using a total amount of data, a working set that's less than the size of your RAM, then it's going to end up all in cache. And the longer the test runs, the more incorrect the results are going to be because it's going to start off slow. And then once it's randomly read every block, it's just going to be reading out of RAM over and over again. And the speed is just going to keep climbing until it reaches literally the speed of your RAM, which could be, tens or even hundreds of gigabytes per second, which again is completely not realistic. So while caching can provide a lot of benefit, when benchmarking, you want to benchmark the worst case as if every time we go to look for something, oops, that's not the thing that's in cache, something else is. And so testing with the caching off will give you much more realistic results. And then the same basically applies to compression, especially if your benchmark happens to write all zeros. You don't want to benchmark with that because it basically means the file system is doing no work except for ignoring all the zeros you're writing. And so you'll get ludicrous speeds that don't make any sense. So you can either just disable compression so that you can keep writing all those zeros, or you can benchmark with uncompressible data, where ZFS will still try to compress it so that you're benchmarking how much CPU it's going to take to deal with writing X gigabytes per second of uncompressible data. And if in the real world, some of that data happens to compress, you get a win. But if it doesn't, you don't have benchmark results that are better than what would actually happen.
Yeah, and as we talked about, configuring your data set and your benchmark to actually be testing the same thing, so that you're not ending up with that write inflation or read inflation, so that at the end of your test, this is what you can rely on. And if you're in a situation where you have a workload and you're not quite sure what would be the best, you can reach out to us and talk about maybe being able to help you with performance audit, which we can talk about later in the webinar.
Yeah. But yeah, sometimes it can even be experimental, right? Trying with your workload on a couple of different record sizes to see what works best. Because, we talked about how the worst case is 4K. Well, also, when you get down to 4K, compression can't help you when you have the smallest possible record size because you can't compress to less than one sector, right? If you have an 8K record and it compresses at least 50%, we can write that as one 4K record. But if you have a 4K record that compresses to 2K, if the sector size is still 4K, you have to take the whole sector anyway, so you might as well not bother with the compression. And if you use an 8K record size and your data happens to compress, 1.5 to 1, well, now it's still 6K, so it still takes the whole 8K. And again, the compression isn't helping. So there are cases, even with databases, where normally you want to try to match up the record size, where a slightly larger record size, like 32K, that's going to compress down to 12K, would be sufficient savings and give you more throughput than just sticking with 8K. But it can really depend on your workload, how often you update a record in place, and so on. But I think the big takeaway here about matching up the record size is that, it's not just the multiple, right? 4K is a lot less than 128K, right? So if every 4K write turns into a 128K write, yes, that's a lot of amplification. But in reality, it's even worse than that. Because first you have to read the whole 128K, even though you're only writing, then modify it in memory and then write it out. So it's not just like 16 times worse. It's 32 times worse and half of it's on read, half of it's on write, plus all the metadata and the processing in memory. It's a huge amount more work than just being able to just directly write chunks of the right size. And when you're doing benchmarks, especially if you're kind of making up your own or using tools specific to an application, like a lot of times applications will have a benchmark for video editing or photo processing or whatever, you want to make sure that the results are waiting for the data to finish writing, right? Otherwise, that write behind can say, oh yeah, we wrote all the data you asked for, but actually 8 gigs of it is still sitting around in memory and being written out in the background right now. And if you didn't include that in how long it took you to write, 128 gigs of data, you're going to get an incorrectly high throughput rating out of your benchmark, and that won't be right.
Yeah, the easiest way to think about right behind is, for anybody that used old USB 2, USB 1 discs, sticks on old computers, you put it in, you try to copy some music to it or whatever, and your file manager would be like, copy done. And then you're sitting there for an hour waiting for the USB to actually finish. It's a similar issue where the data has been written into RAM, but it hasn't quite flushed out to the disk yet. You want to make sure that when you're testing, whatever application you're using to test is actually finally writing all that data out.
Yeah, it literally is the same thing as that, safely eject this device. It's going to wait until it's finished the writes before it says, okay, it's safe. Now we're actually done. And including that, the difference between how long it took to finish the writes at the POSIX layer and how long it took to finish the writes at the physical layer, that difference is going to make a big difference in your benchmark and also affect the truthfulness of your benchmark. So to summarize, take your time when doing benchmarks. Consider what you are testing, right? You want to make sure it's the worst case, but it also realistic, right? You don't have to do a case worse than what it's ever going to be in production, but you don't want to test the happy path. And you want to verify your results up and down the stack. So what the application sees, what the file system sees, what the hardware sees, and anything in between that might be there as well, to make sure that the results you're getting match what you expect, right? The inflation shouldn't be much more than the parity, that it shouldn't be zeros when you're expecting things to be happening, and it shouldn't be, 16 times more writes than you're doing at the application. Otherwise, something's probably wrong. And do the results match what you expect? Right? When you put the system together, you knew how many disks or how many NVMEs you put in it. You knew what the specs were supposed to be. Is it around what it should be, or is it wildly off, either above or below? And figure out what's happening. And if you're having trouble explaining what's happening, you can always call us and we can help you. So we have some time. Oh, sorry. We have a little bit of time for questions. Does anybody have a question? I didn't see any come in via Zoom, but JT, do you want to ask one of the ones from
Yep.
people submitted during registration?
Yeah, so we have a question here. At work, they want to compare performance ZFS RAID Z versus XFS on top of a RAID 6. With their test, they disable file system cache due to the production workload not being cacheable. So I disabled ZFS ARC to have a fair comparison. My gut tells me that this is wrong. Can you outline a better way to compare the two file systems?
So that's probably close to right. I think as we talked about earlier, rather than setting the primary cache setting to off, you would set it to metadata. And that way, ZFS will cache some indirect blocks that it needs to know what it's doing to make up for the fact that ZFS has to do a bit more work than XFS in order to find whatever block it is you're trying to read. But at the same time, have the same effect as disabling the file system cache on the XFS side so that, again, you're comparing apples to apples. The biggest thing will be to, when you're doing these two tests for both XFS and ZFS, to look at, IOStat, not the zpool one, but the actual one at the hardware level, and see how the performance of the file system compares to the performance of the disk. ZFS's will always be a bit worse because ZFS is doing more work, right? It's copy on write means it's writing more things, it's putting them in different places instead of overwriting in place, and a few other things, but it shouldn't be a huge difference. And so this will let you tell that the benchmark you're doing of ZFS is fair compared to the benchmark you're doing of XFS, right? If the hardware, at the hardware level, if the hardware is not doing as much work as it is with XFS, then something's meaning ZFS isn't driving hard enough. And if ZFS is doing like 4 times as much work as XFS is, then something's misaligned somewhere and you are making ZFS work harder than it needs to. And by adjusting a couple things, you can get a fair benchmark to have your bake-off between ZFS and XFS. You want to read one of the other ones?
Yes, so we got another one here. Benchmarking specific ZFS components like particular VDEVs or time spent in operation like checksumming and allocation. Profiling the various paths of the IO path or the various parts of the IO path and finding bottlenecks or optimization areas would be amazing. Are there ways that we can do that, Alan?
So benchmarking a particular VDEV within a pool is not really practical. In general, ZFS spreads writes across the VDEV, so you normally wouldn't be able to do that. Although maybe in this case they mean the type of VDEV. So comparing, a RAID Z1 to a RAID Z3. And yeah, so for looking at the time spent in particular operations like checksumming or allocation or whatever, you can do that with things like dtrace on FreeBSD and Mac or perf on Linux. And we do this type of thing at Clara all the time, profiling a system to see where it's spending the time. Usually checksumming is a very, very, very small amount of the time. And even compression, short of using high levels of Z standard, is usually not a big impact. But it can be, if you have a really small number of CPUs, like an embedded appliance or a small NAS or whatever. And so, yeah, you can definitely be profiling ZFS and look at where it's spending its time, whether that's trying to find where to put data, trying to load and unload the space maps to know which data on disk or which sectors on disk are already allocated versus not, and so on. And so there's a lot that you can look at there. And so, yeah, you know, uh, if you want help with that, yeah, definitely reach out to us via our website and we can help you actually dig into where ZFS is spending its time and how we might be able to optimize that for your workload.
Yep. So we got another one. Is ZFS send receive the same as replication? Is performance generally the same between those tasks?
So it depends if you mean uh, ZFS is, ZFS send receive is the same as ZFS replication. That is basically the components of ZFS replication. In more general terms, replication, it really depends on the type of replication. Like obviously database replication and other file systems are not the same thing. Uh, ZFS send and receive are specifically designed for performance. They are meant to serialize the file system and basically saturate the network to be able to, as quickly as possible, take the contents of a file system on one pool and send them to another pool. And so generally that will be going either as fast as your disk can go or as fast as your network can go, unless there's some other bottleneck, which we could investigate. But in general, those are able to achieve the maximum performance of your system. We have one live question.
Yeah. So someone writes in, ZFS seems to not get close to the expected performance of the underlying NVMe drives.
So is this expected? To some degree, it is expected, basically a known limitation of ZFS at the moment, in that ZFS was designed for hard drives. It does a lot of things to try to optimize for that. For example, right behind we talked about is about taking all the writes you did randomly to all kinds of different files and batching them up into one big fat contiguous write, because that will avoid seeking and maximize the performance of spinning hard drives to write that data out. But if you have an NVMe, you have not that problem, right? Seeks don't cost you anything. And at the same time, you can have, with hard drives, ZFS tries very hard to avoid queuing too many commands to the drive at once. Because, if we're writing out data, say that stuff in the background that's accumulated and we're writing that out, if suddenly somebody comes with a read that the user's stuck waiting until we finish this read, we want that to go to the front of that line. So we don't want to have a lot queued up on the hardware. We keep it queued up on ZFS so that ZFS can decide to let certain IO cut to the front of the line. With NVMe, instead of one queue of maybe 32 or 64 commands, a normal NVMe drive will have 63 queues that can each hold 64 commands. And the spec would allow up to 64,000 queues of 64,000 commands, although there's no such device yet. But in order to keep an NVMe busy, because the amount of time it takes to do one IO can be microseconds instead of 4 milliseconds like it is on a hard drive, ZFS needs to keep a lot more commands outstanding to the disk, and it wasn't really built for that. And so there's work going on now, but if you have a specific use case, definitely get in touch with Clara, and we can look at how to get your NVMe performance much closer to what it says on the box that your NVMe came in compared to what you're getting today. There's still lots to be done, but there's a lot more of the performance can be had today. And then, in the future, we expect to be able to actually get most of what's expected out of these NVMe drives. But do remember, like we talked about when comparing ZFS to XFS, ZFS does have to do more work. And so it's not necessarily always going to benchmark the same as the maximum that could be there. But what you're getting for that trade-off from ZFS is the guarantee that your data is correct, whereas every other file system is not doing that.
Yeah, ZFS has a lot of tuning parameters that you can go in and tweak some variables. Be warned that if you just start going in and madly changing those values, you can end up in a very worse situation. But there are ways that you can tune ZFS to get better performance out of NVMe that is available kind of in the code today. And actually that leads into the next question we had, which is what is the best way to troubleshoot and diagnose ZFS performance issues? How can I determine what knobs to twist and where there are no more knobs to twist?
Yeah, that's a hard question. That a lot of time comes down to experience and knowing where to look. But most of the time, it is kind of these same things we were talking about with the benchmarking of looking at, what are we seeing at the application level versus what we're seeing at the disk level. There's a big difference between those two. Why? And digging into it. Or what we're talking about with the NVMe. If the problem is that the NVMe is taking too long to do the work, or is the problem that the NVMe is spending the last half of every second idle because ZFS isn't feeding it enough work ahead of time? Because ZFS is worried about causing too long of a latency on a read, but it turns out the NVMe is so fast that ZFS just can't keep up. So there's definitely no one right answer other than there's our website. But yes, there's a lot that can be done, and if you reach out, we can definitely help you through those steps. So thank you for joining us. That completes our session today. It was great to have you all, and we hope that you found this discussion very insightful. If you have any follow-up questions or need to learn more about Clara or need help with ZFS or FreeBSD, please definitely do reach out to us. Be sure to keep an eye on our webinar page and social media channels as we have more webinars coming up. If we try to regularly host these webinars about once a month on key topics and challenges, and we'd love to see you all again. And if you have an idea, a topic suggestion for a future webinar, also please let us know. Thank you very much.